Welcome to Microlecture 49, another alkene addition reaction. This time it's hydroboration-oxidation. Okay, so for the addition of BH3 to alkenes, you'll want to be able to draw out the transition state structure, so I'll show you how to do that on the last slide. First, we'll talk about how to predict the regiochemistry. So in this case, that means which atom the OH adds to. And the stereochemistry, here we're going to learn some new terms, syn or anti-addition. So since we're adding two things simultaneously to the carbons of the carbon-carbon double bond, we can talk about whether those two things add on the same face of the double bond or opposite face. Okay, so syn and anti are new terms there. The addition of OH across the carbon-carbon double bond in this case is indeed going to go syn, and that'll be because of the mechanistic details, and that's why it's important for you to understand the transition state structure for the first step, adding the BH3 across the double bond. So for now, let's just talk about the predicted regiochemistry and stereochemistry. And so through the course of this reaction, the double bond is going to react such that we are going to add an OH group to the less substituted side and H to the more substituted side. So that's opposite the way that we have been doing this type of addition of OH across a double bond. And therein lies the utility of this reagent set. So if we want to synthesize an alcohol that's less substituted, then this would be the way to go. As far as the stereochemistry goes, we're going to see that the OH and H do add syn. That means that there's going to be some stereochemical consequence here. Being that they add to the same face of the double bond, they're each going to be shown, or they're both going to be shown on dash, or both going to be shown on wedge, one or the other. And then you can go ahead and fill in anything else that is there. There's a methyl here that I was missing, and then on the end carbon here, we've got just hydrogen atoms that that we could draw in just for clarity. Okay, so the process is syn, and in this case, we do have a chiral center. So it's important to be able to show that because what we start with is flat, okay, that we can also end up with the H and the OH approaching from the opposite side of the flat alkene. So they could have ended up on dashes instead of wedges, okay, which changes the rest in the following way. And so basically what that means is that we end up with a 50-50 mix of enantiomers. The product, therefore, is considered a chiral. Okay, so let's do some more examples here. The THF, by the way, is just a solvent. So when we talk about the mechanistic details, it's primarily just going to be involving BH3. And we don't talk at all about step 2, but that's the part where the OH is actually added, and you do not need to know the mechanism or any mechanistic details for step 2. Alright, so predicting the product for this 5-member ring structure, the OH is going to add to the less substituted side, and H to the more substituted side, and they're going to add syn. So on the same face, we could draw them both on dash. That's going to force the methyl group to be on the opposite face, so it's going to be on the wedge. But with equal likelihood, the BH3 can approach the alkene from the opposite face because this structure is flat or planar, and there's no groups coming in or out of the plane at all, right? So with equal likelihood, we could have the OH group and the hydrogen form on the opposite face. Okay, forcing the methyl to be back in that case. these happen to be a 50-50 mix of enantiomers. And it's for that reason that this sample would be achiral. It would not be optically active. Of course, we started with something achiral, and so that makes sense. In the next example, though, we're going to see that we have a nearby R group on a wedge, actually, and this R group is going to dictate the stereochemistry and the stereochemical outcome, all right? Because the BH3 cannot approach from that face of the alkene, the wedge face, if you will, or the face that's on our side if this isopropyl R group is coming out of the page at us. The BH3 would have to approach the alkene from behind. And so that means that while we get syn addition, it's going to happen on the opposite face of this isopropyl group, right? And so my OH is going to form on the less substituted side, my H on the more substituted side, and it's dash only this time. We do not have the opportunity to put the OH and H group on the same face as this nearby R group. And then I'm going to actually redraw my ethyl group so it makes stereochemical sense. Here on this carbon atom, I can't have 3 bonds drawn planar on lines, right? In order to show if this was an R center or an S center, I have to do better than that. So I have to show it as a tetrahedral center with 2 bonds that are in the plane, 1 bond that's back or dash, and another bond that's wedge. So this ethyl is actually forced now to be on the wedge, and that allows us to determine the absolute stereo configuration of that chirality center. All right, and this is the only product that is formed, so it is a chiral product. Notice that we started with something that is chiral because we have a chirality center here, and so we are ending with something that's chiral. Something to watch out for. All right, so in the first case, we have 2 expected products. In this second example, we have only 1 expected product. And then the last example here, we have an alkene that has some stereochemistry associated with it. So we're noticing that these 2 methyl groups are on the same face of the carbon-carbon double bond. That's going to help us. It's an aid or crutch, if you will, to kind of keep track of that and draw the product with those 2 methyl groups situated that way, so that if you're asked to figure out the absolute stereo configuration, R or S, for the product, that you would get it correct. So the borohydride can approach from either face of this flat structure. But I'm going to keep drawing the methyl groups sort of on the same side in terms of like E or Z, right? So, so this is an E alkene with high priority group up there and high priority group on this side down here. And so we want to kind of keep that relationship between the groups. All right, and so hydrogen adds to the more substituted side, OH to the less substituted side. It happens syn. And so if I draw now proper tetrahedral centers, this ethyl group is on the wedge. All right, but with equal likelihood, okay, and so I've kept my relationship between the methyls. With equal likelihood, the borohydride, the BH3, could have approached from the opposite face of the molecule, and so we could have ended up with this as a resulting product too. Okay, these are 50-50 mix. of enantiomers. It's a racemate. It's achiral. Alright, so we would expect to form both possible products here. And if you were to be asked to figure out the stereochemical designation of that center, is it R or is it S? Looks to me like it would go 1 to 2 to 3 in a clockwise direction. Yeah, so that's R. So the mechanistic details here, what I'd like you to be able to do is draw a transition state structure that helps explain why it's syn addition. Okay, so what that's going to look like is, well, the BH3 approaches the molecule so that the boron is situated farther away from any R group. All right, so if we have an R group, on the more substituted side of this carbon-carbon double bond, then the boron's going to situate itself on the opposite side of that. That's the bulkier side of the BH3 molecule. But the H, the little hydrogen, is going to situate itself closer to the more substituted side of the carbon-carbon double bond. So this is our bond breaking. That's the carbon-carbon double bond breaking. The less substituted side is going to form a bond to the boron. The boron-hydrogen bond here is going to break. So we're drawing these half-broken, half-formed bonds with dotted lines. And the hydrogen is going to add right here to the more substituted side. All right, and then without having to know the mechanism, what happens on the side of the boron is that the boron, the BH2, is displaced by an OH group. Okay, but that happens in the second step with hydrogen peroxide and KOH. Right? So this is the transition state structure. It's a box-like structure, and it explains why we get syn addition, and it explains why the OH group adds to the less substituted side. Okay, because the bulkier part of the BH3 molecule is going to end up on the less substituted side of the alkene. Okay, and so once again, once the BH3 has been displaced by the hydroxide, what we end up with here is H there and OH there. Okay, and it's achiral, not because there isn't a stereocenter, there's two of them, but it's because we get a 50-50 mix of enantiomers.